In April 2025, a team of astronomers announced something that briefly stopped the entire scientific community in its tracks. In the atmosphere of a planet 124 light-years away, the James Webb Space Telescope had detected the possible signature of a gas that, on Earth, is only ever produced by living things. Not maybe life, not a vague hint at a specific molecule, dimethyl sulfide, that, as far as we know, has exactly one natural source on our own planet: ocean phytoplankton, the microscopic marine life that quietly pumps this compound into our atmosphere every single day. Finding it somewhere else, on a planet we've never set foot on, orbiting a star we'll never visit, would be one of the single most important discoveries in the history of science. Except almost immediately, other scientists started pushing back. Not with dismissal, with data. Multiple independent teams reanalyzed the exact same observations and came to a very different conclusion. Maybe the signal isn't there at all. Maybe it's noise. Maybe it's something far less exciting explaining the exact same numbers. More than a year later, that argument still hasn't been settled. This is the story of K2-18b, the planet that, for one brief moment, looked like it might answer the biggest question humans have ever asked, and why the scientists who study it most closely still can't agree on what they actually found. It's worth being upfront about something before we go any further. This video isn't going to end with a clean answer, because there isn't one yet. What it will give you is the full, honest picture of exactly what was found, exactly who's disputing it, and exactly why this specific disagreement matters more than almost any other open question in astronomy right now. To understand why this single measurement caused such an uproar, you first need to understand exactly what kind of planet K2-18b actually is, and why it became a target for this search in the first place. K2-18b orbits a small, cool red dwarf star called K2-18, located about 124 light-years from Earth in the direction of the constellation Leo. It was first discovered in 2015 by NASA's K2 mission, the repurposed continuation of the Kepler Space Telescope after part of its stabilizing hardware failed. At the time, it was just one entry in a long list of newly confirmed exoplanets. Nothing about the initial discovery suggested it would become one of the most talked about worlds outside our solar system a decade later. What makes K2-18b interesting is its size and its orbit. It's roughly 8, 6 times the mass of Earth and about 2, 6 times Earth's diameter, large enough to place it in an entirely different category than our own planet, somewhere between rocky worlds like Earth and gas giants like Neptune. Scientists call this size range a subneptune, and it's actually the most common type of planet astronomers have found anywhere in the galaxy, even though our own solar system doesn't have one. Crucially, K2-18b orbits within its star's habitable zone, the distance from a star where temperatures could theoretically allow liquid water to exist on a planet's surface. That single fact, combined with its size, led Cambridge astronomer Nika Madhusudan and his research group to propose, back in 2021, an entirely new category of potentially habitable world, a Hycean planet, short for hydrogen and ocean. The idea is that a planet like K2-18b could have a thick, hydrogen-rich atmosphere sitting on top of a genuine liquid water ocean, creating conditions that, at least in theory, microbial life could survive in, even without a solid rocky surface like Earth's. K2-18b became the prototype test case for that entire idea. If a Hycean world existed anywhere, this was the leading candidate to check. In 2023, using JWST's near-infrared instruments, Madhusudan's team detected methane and carbon dioxide in K2-18b's atmosphere, a genuinely solid, well-supported finding, while notably not detecting ammonia, which was interpreted as being consistent with a deep water ocean absorbing it below the visible atmosphere. Tucked into that same 2023 data was something else, a faint, low-significance signal that looked like it might be dimethyl sulfide, sitting at just 2. 4. Sigma confidence. For context, in physics and astronomy, a real discovery typically requires 5 sigma, meaning less than a 1 in 3. A 5 million chance the result is a random fluke. A 2. 4 sigma signal, statistically, could plausibly just be noise. Even the team that found it described it carefully as tentative. It's worth understanding exactly how a measurement like this is even made, because the process itself explains why the results are so hard to pin down. K2-18b doesn't reflect enough light for scientists to photograph its surface or atmosphere directly. Instead, JWST watches the planet pass in front of its host star, a transit, and measures how starlight filters through the thin ring of atmosphere around the planet's edge on its way to Earth's telescopes. Different gases absorb light at very specific wavelengths. So by measuring exactly which wavelengths get dimmed slightly more than others during a transit, scientists can work backward to figure out which molecules are present. The catch is that this signal is extraordinarily faint to begin with, a sliver of starlight passing through a paper-thin atmospheric layer around a planet 124 light-years away, and separating a genuine chemical signature from instrumental noise, contamination from the host star's own activity, or subtle calibration effects becomes an exercise in statistics as much as astronomy. That difficulty is exactly why the same raw data can be interpreted differently by different teams using different analytical choices. That should have been the end of it for the time being. An interesting hint, worth checking again with better data. Instead, it set up exactly what happened 2 years later. In April 2025, Madhusudan's team went back to JWST, this time using a different instrument called MIRI, tuned to a different part of the infrared spectrum, the 5 to 12 micron range, distinct from the near-infrared data used in 2023. And this time, the signal came back stronger. Spectral features consistent with dimethyl sulfide and a closely related compound called dimethyl disulfide. At a confidence level, the team reported as 3 sigma. 3 sigma is a meaningfully different number than 2. 4. It represents roughly a 99. 7% confidence level, genuinely striking for an exoplanet atmosphere measurement, and strong enough that Madhusudan's team felt confident enough to publish it publicly and describe it as potentially the strongest evidence yet for a biosignature beyond our solar system. Because this new detection came from a completely different instrument and a completely different wavelength range than the original 2023 hint, it initially looked like independent confirmation, 2 separate measurements pointing at the same conclusion. To put the scale of this claim in context, here's why dimethyl sulfide specifically was chosen as the target molecule worth searching for. On Earth, it is produced almost exclusively by marine phytoplankton and certain bacteria, released into the ocean and eventually into the atmosphere as part of the natural marine sulfur cycle. It doesn't form in meaningful quantities through volcanic activity, geological processes, or ordinary atmospheric chemistry here on Earth. That's exactly what makes it a candidate biosignature gas, a molecule whose presence, if verified, and if abiotic explanations can be ruled out, would be difficult to explain without invoking biological activity. But here's the number that made this claim so extraordinary and so immediately controversial. For dimethyl sulfide to be detectable at the levels JWST appeared to be seeing, models suggest K2-18b's hypothetical biosphere would need to be producing the gas at a rate roughly 20 times higher than all life on Earth's oceans combined produces DMS today. That's not a small ask. That's an entire planet's ocean ecosystem operating at a pace far beyond anything we've ever observed happening on our own world, which is exactly the kind of extraordinary claim that fairly demands extraordinary evidence before anyone accepts it. And that's precisely where the scientific community split. There's one more wrinkle worth mentioning before getting into that split, because it makes the story more complicated in an interesting way. Dimethyl sulfide isn't actually unique to living things in every corner of the universe. It just happens to have no known significant non-biological source on Earth specifically. Separate research published in 2024 and 2025 found trace amounts of dimethyl sulfide in material from comets in our own solar system, and even detected it drifting freely in the interstellar medium between stars, produced through pure chemistry with no life involved at all. That doesn't mean the K2-18b signal, if it's real, is definitely non-biological. The conditions on a comet or in the near vacuum of interstellar space are wildly different from a planet's atmosphere sitting above a warm ocean. But it does mean the only life makes this argument that made headlines in April 2025 is a little more complicated than the original framing suggested. And it's part of why some researchers wanted to test alternative chemical explanations before accepting the biological interpretation. Almost as soon as the April 2025 announcement went public, other research groups began independently reanalyzing the same raw JWST data, and the results did not line up neatly behind Madhusudan's conclusion. A team led by Raphael Luque at the University of Chicago published one of the most direct challenges, working with the full combined dataset from 3 separate JWST instruments, NIRIS, NIRSPEC, and MIRI, rather than any single instrument in isolation. Luque's team found no statistically significant evidence for either dimethyl sulfide or dimethyl disulfide anywhere in the spectrum. Their analysis did confirm the presence of methane at high confidence, consistent with the original 2023 findings, but the specific sulfur compound signal that had generated the biosignature headlines simply didn't hold up once the complete dataset was analyzed together rather than piece by piece. Luque was careful in public comments to frame this as a matter of scientific rigor rather than dismissal of the search itself. As he put it in a public statement, if a more mundane, already known molecule can explain the same data, science shouldn't reach for an exotic explanation before ruling out the ordinary ones first. He and his team have specifically pointed to ethane, a much more common non-biological molecule already known to exist on planets and moons throughout our own solar system, as a plausible alternative explanation for the same spectral features that had been interpreted as DMS. A separate reanalysis by researcher Jake Taylor reached a similar conclusion using different statistical methods. Again, finding the original detection was not robust. Researchers Louise Wellbanks and collaborators went a step further, arguing that the original 2025 detection depended heavily on a narrowly constrained set of candidate molecules built into the model used for the analysis, meaning the specific list of gases the original team chose to test for may have shaped which conclusion the data appeared to support, rather than the data unambiguously pointing to DMS on its own. Then, in July 2025, a NASA-led study added yet another data point to the debate. That analysis confirmed K2-18b's genuinely water-rich, complex atmosphere, supporting parts of the original Hycean world picture, but explicitly found no conclusive evidence of dimethyl sulfide, while acknowledging just how difficult these kinds of faint atmospheric signals are to interpret correctly, even with JWST's unprecedented sensitivity. It's worth being precise about what these reanalyses actually did and didn't find, because the nuance matters. None of the challenging studies claim K2-18b's atmosphere is simple or fully understood. Several confirm methane at high confidence, and none dispute that the planet likely has a genuinely unusual water-rich atmosphere unlike anything in our own solar system. What they specifically dispute is the sulfur compound signal, the one piece of the puzzle that would have pointed toward biology rather than ordinary planetary chemistry. That's an important distinction. This isn't a case of one team saying there's nothing interesting here against another team insisting there is. Every team agrees K2-18b is scientifically remarkable. The disagreement is narrowly, specifically, about whether one particular gas is really present at the levels needed to suggest life. Madhusudan's team hasn't simply conceded the point either. They've continued defending the statistical basis of the MIRI detection, arguing that a real signal is present in that specific data set, even if it doesn't survive being combined with data from other instruments in every reanalysis. As of the most recent published research, the two sides of this debate haven't converged. There's a genuine, ongoing disagreement between credentialed teams working from the exact same publicly available JWST observations, reaching different conclusions depending on which instruments they combine, which statistical methods they apply, and which set of candidate molecules they test the data against. That's what makes this a real scientific mystery rather than a manufactured one. Nobody is claiming this is confirmed. The scientist who found the signal is still defending it. Multiple other well-credentialed teams say the data doesn't support it, and the gas in question, if it's really there, would represent one of the most significant discoveries in the history of astronomy. The stakes of getting the answer right, in either direction, are enormous. It's worth stepping back and asking why this specific disagreement over one faint signal in one planet's atmosphere deserves so much careful scrutiny instead of just being reported as a straightforward discovery. Because the history of science is full of exciting announcements that didn't hold up, and also full of real discoveries that were initially doubted. Getting this specific question right matters enormously in both directions. If dimethyl sulfide really is present in K2-18b's atmosphere at the levels originally claimed, and if abiotic explanations really can be ruled out through further observation, it would represent the first serious scientific evidence of life existing anywhere beyond Earth, arguably the single most consequential discovery any species has ever made about its place in the universe. That's not something responsible scientists rush to declare based on a 3 sigma signal from one instrument. But if the signal isn't really there, if it's an artifact of how the data was processed, or better explained by a common non-biological molecule like ethane, then prematurely declaring a biosignature discovery risks a genuine scientific embarrassment, the kind that erodes public trust in exactly the sort of careful evidence-based process that makes real discoveries credible when they do eventually happen. Researchers on both sides of this debate have been explicit that the goal isn't to win an argument, but to get the actual answer right, because the stakes of being wrong, publicly, on a question this significant, are genuinely high for the entire field. That's also exactly why the disagreement itself is scientifically healthy, even though it can look messy or inconclusive from the outside. Independent teams checking each other's work, using different statistical approaches, testing alternative explanations, and openly publishing disagreements in peer-reviewed journals, all of that is the scientific process, functioning exactly as it should when the potential discovery is this significant. It's slower and less satisfying than a clean, dramatic announcement, but it's also the only process that actually produces reliable answers to questions this important. And the story isn't over. JWST continues to observe K2-18b, and additional observation time has already been used to gather more data specifically aimed at resolving this exact disagreement. Future analyses, combining more observations across more of JWST's instruments, may eventually settle whether dimethyl sulfide is really there, or whether this entire debate turns out to be a lesson in how easily even world-class instruments and world-class scientists can find themselves looking at the very edge of what current technology can reliably measure. This wouldn't be the first time an exciting biosignature claim didn't survive scrutiny, and it's useful context for understanding why scientists are being so careful this time. In the 1970s, NASA's Viking landers on Mars returned soil test results that briefly looked like they might indicate microbial metabolism, before follow-up analysis attributed the results to reactive Martian soil chemistry instead of biology. More recently, phosphine gas detected in the atmosphere of Venus in 2020 was initially proposed as a possible biosignature, since phosphine has no simple abiotic source on rocky planets, only for follow-up studies to dispute the original detection entirely, in an argument that, in some ways, closely mirrors what's happening with K2-18b right now. Each of these cases became a genuine learning moment for the field, refining how researchers verify extraordinary claims before the next one comes along. K2-18b is, in a sense, the most recent chapter in that same long, careful process. So here's where this genuinely stands right now. In 2023, a faint hint of dimethyl sulfide showed up in K2-18b's atmosphere at just 4 sigma confidence, weak but intriguing enough to take seriously. In April 2025, using a different JWST instrument, the same research team reported a stronger signal at 3 sigma confidence and described it publicly as potentially the most compelling biosignature evidence found anywhere outside our solar system. Since then, at least 4 independent reanalyses from teams at the University of Chicago, from other researchers reprocessing the same public data, and from a NASA-led study, have all failed to confirm that signal using the complete combined dataset, with several pointing to ordinary non-biological molecules, as an equally good or better explanation for the same numbers. The original team has not backed down from their interpretation of their own specific dataset. Neither side has definitively won this argument yet, and the reason that matters is simple. This isn't an academic dispute over a minor detail. It's a live, unresolved disagreement over whether humanity may have already detected indirect evidence of life on another world, or whether we're looking at an ordinary atmospheric chemistry story that got ahead of itself in the excitement of the moment. JWST is still watching K2-18b. More data is still coming in. At some point, probably within the next few years, either the signal will strengthen into something undeniable across every instrument and every method, or it will fade away entirely as more observations rule it out. Right now, in 2026, we're still in the middle of that process, watching one of the most important open questions in modern astronomy play out in real time, in public, across competing peer-reviewed papers. If you want to know the moment this actually gets resolved, whether K2-18b turns out to be the first real evidence of life beyond Earth, or a cautionary tale about how easy it is to overinterpret faint data, subscribe to the channel and turn on notifications. Because when new JWST observations come in, we'll break down exactly what they show, with the real data, not the invented version. One planet, one gas, one disagreement that could change everything, or nothing at all. Thanks for watching.